Oh, and starting from today, I'm just going to directly record to cloud. And because of Canvas, right now I also add a Zoom information on Canvas, so you can directly come to class, click that Zoom link. And but initially I thought I recorded to cloud, and then Canvas will automatically put the link to that Zoom session. But then yesterday I found out, because yesterday I just started with my 2 other class, I found out that's not the case. So in order to find our class recording, you still need to go to my module, each module's Zoom class recording. Okay. So that's the general information regarding Zoom. So today we will start with some new topic. Okay, the new topic is going to discuss, hold on, why this not, this pen, okay. It's about to discuss some sorting algorithm. Not all of them, because there are quite a number of sorting algorithms, okay, but we are going to discuss some basic ones. You mean that Zoom link doesn't work? Oh,
she means that we have to copy paste it, like we cannot click on it.
Oh, I need to double check.
The link is correct.
Okay, I need to double check with everything. Oh, this Canvas said it automatically. I just do import, then oh. There are all sorts of, because Canvas is it's new. Okay, we just started, so I needed to find out everything. But anyway, so today we are going to start with discussing about sorting algorithms. Okay, and so here our discussion is array based. But of course, it will be very easy to be switched to like array list in Java, okay? And the first, if you want to read a textbook, it's chapter 23, I believe, okay? And the very first sorting algorithm we are going to discuss is called bubble sort. Bubble sort. Another name is called exchange sort. Okay, so the idea, so let's use a sequence of number to explain how it works. Okay, suppose I have number 69, 35, 18, 87, 50, 58, 79, etc. So all these integer numbers are randomly placed in an array, suppose, okay? And I want you to sort in ascending order. In ascending order. So the first algorithm we discussed today is called bubble sort. So how that algorithm going to work, okay? So bubble sort involves a number of passes or rounds. Okay, in the first pass, what we are going to do is we are going to do pair by pair comparison. So I compare these two. And because 69 is greater than 35, and you're going to sort in ascending order, so I need to switch those two numbers, okay? So here is 35, then this is going to be 69. And then you move on to the next pair. So you compare now 69 to 18. It's still not in order, is it? So I'm going to switch those two numbers, 69. And then you compare the next pair. So this is already in order, is it? So no switch, no swap. Then you move on to the next pair. So it's not in order. So I switch 87, is it? And I move on to the next pair comparison. So it's not in order. So 58 and 87. And then I move on to the next pair. Is it in order? No. So then I swap 79, then 87. Okay, let me rewrite after this first pass, okay, per first round. So what we have is going to have 35, 18, 69, 50, 58, 79, 87. Is it? So this is after you finish a pair by pair comparison from the beginning all the way to the end. Is it? All the way to the end. So anyone find any specific pattern here for this sequence of number after the first pass? Anyone find a pattern? Take a look at this number. Any specific thing regarding this number 87?
It's the largest out of the group.
Very good. It's the largest one. For some reason I cannot write it. The largest one, is it? Where the largest one is at?
At the end?
And
Yeah, the largest one is at N. Is it? So after the first pass, the largest one is at end. Is it at end? So basically it is already in place. Is it in place? Then if you think, if you keep using this kind of operation for all of the remaining numbers, then let's take a look over here, okay? So we can exclude this number out. Is it? Because this is already in place. Then we can exclude it, but we still need to think about, so suppose this is number n, then this n minus 1 number, they are not in order yet. So you still need to sort them. And just think about, then we can do the same thing, is it? You can do pair by pair comparison. And if there is a need, then you can swap. Is it? You can swap. Then just think about after the second pass. After the second pass, which number? So here is 87. How about the second largest? Is the second largest number going to be at the second, the reverse second place?
Yes.
Where the, yeah, it is supposed to be here. Is it? Second largest number is who? Is 79. Is it? So let's try. Let's try to do this again. Okay, so we do pair by pair comparison, is it? So we need to swap those two numbers. Then we move on to the next 35. It's already in order, is it? Then we compare the next, it's not in order, so we need to swap. And then you switch to the next pair, it's not in order. then you need to swap. Then you compare the next one, it's already in order. Is it? So 79 does get put at the second place, reverse order. Is it? So it's placed in its place. And the remaining numbers, we can copy it down. 18, 35, 50, 58, 69. So after the second pass, then the last two numbers sorted. Is it sorted? Then in the next pass 3, then you can keep doing this. Is it? So this kind of pattern, after each pass, then one of the largest number going to be placed at its right place. Then, so each pass, you shorten the sorting list by 1, kind of. Is it? Kind of. There until, and who can imagine when should end, generally speaking? When will be the termination condition? Who can imagine?
When no changes appear after you
Yeah,
go
with no change is, yeah, it's one case. Generally speaking, suppose you always need to do sort. Suppose the list, we call this a sublist. Is it? Suppose the sublist is never sorted. Then you need to keep doing. Then what will be the termination condition?
When n equals 1.
Very, very good. Yeah, when the sublist size is 1. Is it? So you can keep shortening, and when the sublist is just as 1 item, then definitely, because all of the items after it, it's already sorted. Is it? That's the general condition, termination condition. Okay. Okay, and then let's come back to what I believe Alex has just answered. The other termination condition, let's take a look at this specific case. Is there any swap needed? No. Any swap needed? No. Any swap needed? No. Any swap needed? No. Okay, there is no swap needed. Okay, so here the question is, if no swap needed, what that tells us?
The list is already sorted.
Yes, very good. So that means it's already sorted. Is it? So do you still need to continue? No. Is it?
No.
So that's another termination condition. Is it? Either the list size is 1 or there is no swap needed. Is it? Then that means your list is already sorted. Is it already sorted? Okay, so this is the idea. We call it a bubble sort. And there's another name called exchange sort. And we can understand why it's called exchange sort, because you do pair by pair comparison. And then you swap. That's why we call it exchange. And why it's called bubble? Bubble is why? It's the largest one always sync to the end for each sublist. Is it? So it's kind of like you throw a stone to the water. It's sink to to the bottom. Is it a bubble? Is it? That's why we call it bubble sorting. Okay. Okay, so this is regarding bubble sort. And for bubble sort, let's then, can you think about what will be the best scenario? So what the best scenario means?
If the list is already sorted.
Yeah, so means fewest pass. Not pass, fewest pass. Is it? So basically just one pass will solve the issue. Is it? What's that case? If the list is already sorted. Is it? Just think about if your whole list is already sorted, you just compare and you know it's sorted. So that's it. It's done. Is it? And then just think the other way. If the list is in reverse order, what's going to happen?
We will have the maximum amount of passes.
Yeah, so that will need the maximum number of passes. Very good. Yeah, okay. And the average is just random, is it? Because this, if we understand this, then next chapter, it will help us understand some other concept, okay? So, okay, so how about a bubble sort? Does it make a lot of sense now? The first algorithm, bubble sort. Okay, so then next, let's start with the second sorting algorithm. Is about, we call it a selection sort. And later on, we will take a look at coding. Okay, selection sort. So same thing, let's take a look at this example. We have 69, and then we have 35, then 18, then 87, 50, 58, 79. Okay, so same thing, same sequence of number as the other one, but this time we are going to apply a new algorithm called the selection sort. So let's see how it works. So initially, so pass one is what? In the whole sequence, you find the smallest number. So 18 is the smallest. And if 18 is the smallest, so still in ascending order. If 18 is the smallest, where it is supposed to go? It's legitimate condition, location in ascending order, where it should go.
The beginning.
Yeah, so it should go to the very beginning, is it? So then you swap these two numbers. So 18, 69, is it? So let's rewrite it as 18, 35, 69, 87, 50, 58, 79. Is it? So after we find the smallest number and swap it with the number that it's supposed to be, then we get this new arrangement, is it? But 18 already in its place, is it? So it's already sorted. And the remaining, this sublist, this not sorted yet. Is it not sorted yet? Okay, then pass 2. We can do same thing on the sublist. Because we can ignore this. It's already sorted, is it? So we ignore the first number. So we start from the second number. And this time, who is the smallest? This is the second smallest, is it? So it's the smallest in sublist. And it's supposed to be where? Supposed to be here. So it's already in its place, is it? So no swap needed at this phase. So we can clear it. 87, 50, 58, 79. So then after the first two pass, then the first two number already sorted, is it? And this is unsorted list. Sorted, is it? Then we can keep doing. What's the next number? The smallest number in this sublist? 50, is it? So is 50 in its place? It's not, is it? So you are going to swap these two numbers, 50 and 69, is it? And you can keep doing this. And when do you view this should terminate? This kind of passes. When it should terminate for this selection sort.
When the sublist is sorted.
When the
When there
sublist,
was no swap.
so you mean when sublist is sorted?
Yeah.
But
When it's
how do
like
you know if
smallest to largest?
how do you know the sublist? Because you see, in this whole algorithm, we didn't discuss, we didn't detect if it's sorted, is it? What we, each pass, the goal is to what? Goal is to find what? Each pass, the goal is to do what? To find the smallest item, is it? And check if it is in place. That's it. So we don't know if it's sorted or not like the bubble sort. Is it a bubble sort to keep a compare? Here you didn't, you just find the smallest. That's your goal. So it's different from bubble sort. So that's not the termination condition. So this doesn't matter to us. Even though the whole list is sorted, it doesn't matter. Okay, let's check what the chat said. Yeah, very good. Said no, doesn't mean, yeah. Oh, someone said, yeah. Okay. So someone answered, is it when the sublist size is 1, is it? When you only have a single item, that's the smallest in its sublist, is it? So that's the single termination condition, okay? In selection sort, okay, in selection sort. Okay, then in selection sort, then does it matter like the list is sorted or in reverse order, or it's just random?
No.
Yeah, so it doesn't make a huge difference, okay, compare with the bubble sort, is it? So it doesn't matter too much. But if you compare selection sorting and the bubble sorting, bubble sorting is good in what kind of scenario? If your list kind of already or majority part already sorted, is it? Then it's better than selection sort, okay? Okay, so this is the second sorting algorithm. And then the third one, yeah. Third one is called insertion sort. Insertion sort, okay. Insertion sort, let's take a look, the same example, okay, same example. So we have 69, then we have 35, and we have 18. We have 87, 50, 58, 79. Okay, so what insertion sort mean? Okay, insertion sort, you need to pick a key for each pass. Okay, so over here, we start at the second number. So this is the key. Okay, this is a key. And then, and the insertion sort, then you need to compare the, you need to get basically, this is the key, and you need to get the key, get a key to its right place, to its right place for the numbers ahead of it. I shouldn't say ahead. So for the numbers that left to it. Left to it. Okay, so then let's see. So in this case, this is the key. And the left to it, it only has 69. It only has 69. So 35 in its final location, it should be ahead of 69. Is it? So you need to place 35 at 69 location and then shift 69 one spot. Is it? Then you place 35 to its right location. Is it? So after we do that, we have 35, 69, 18, 87, 50, 58, 79. Is it? So after, so this is the key position. Is it? The key position, then the left. So basically, with this key position, you kind of have two sublist. To its left, this is in right place. Is it? So what we mean here is sorted. Is it? Sorted. And for its left or for its right, it's unsorted. It's unsorted. Is it? So then we need to move to the next phase. Okay, so I'm going to use a different color. Okay, so the next phase I'm going to, so this is going to be of a new key position. UK position. So this is 18. Is it? This is 18. And for 18, then you need to get it to the right location. Is it? To its all of its left numbers. Is it? Of its left sublist. Is it? So then you compare, you're going to do one by one compare. Is it? So is it in the right? No. Is it? So you're going to shift. Is it? So 18 is going to be here, and the 69 is going to be here. And then you need to compare. Is it? And you still need to shift. Is it? So after this shift, you're going to have 18, 35, 69, 87, 50, 59, 79. Is it? So this is the current key. Is it? And you have two numbers. So to its left, all of them are already sorted. and to its right, it's unsorted. Unsorted, is it? And you keep doing like this. So each time you move down your key, and then you need to get that number to its right place so that you can make sure all of the numbers on its left are sorted and all of the numbers to the right are unsorted. And you keep doing this until the last one is the current, is it? Then you don't have any now because all of its left already sorted and the right doesn't have any numbers. So that means every number is already sorted in its right location. So this kind of concept is called insertion sort. Okay, insertion sort. Okay, but for this insertion sort, you can see it involves a lot of compare and shifting. Is it shifting? And it's kind of slow when you do this moving, shifting. Is it? Each time you just move one, shift by one, and keep shifting by one. Is it? So there is another kind of sorting that's based on insertion sorting, but to try to move faster. Okay, because for this case, if the sequence of number is not large, okay, so if sequence of number is not large, and this kind of slow doesn't matter a lot, is it? Because it's compare and the shifting is kind of slow, is it? And if some number, you know, some unsorted number, suppose here is 1 is at the very back end, is it? They take so many moves to get to the right location, is it? It's very slow, okay? So slow to move the item to its right place, is it? It takes slow, especially if you have like this one that's very small, supposed to be at the very beginning, is it? Especially if the item is farther away from its right place. Especially in this case, is it? It's going to be slow, okay? So because of this, so there is another similar, but it's a little bit different. Okay, so let me find it. But I need to use let me try to use a different set of number. Okay, so it's a enhanced, we can see, sorting. We call it share sort. Share sort. Okay, so let's take a look at this sequence of number. I will use more. Okay, 62, 83, 18. Then I have 53. I have 7, and then 17. Then 95. Then 86. Then 47. And 69, and 25, 2080. Okay, 28. So this time I have sequence of number. Okay, so I will use some similar insertion sort. So it's based on insertion sort. based on insertion sort, but with multiple gaps. Oh, not gaps. Okay, so what does that mean? In insertion sort, the gap size is 1. Okay, it's 1. That means when you do that compare, when you do shift, is it? You just do 1. Okay, and then the issue is if the number is farther away from it's supposed to be located, it takes quite a while to move it to its right location. Is it? Then people think, because the researchers are okay, so can we choose some larger gap size? Larger gap size, okay. So in this case, we will start like the gap size. Start at 5. At 5, okay, suppose I call gap equals 5. Okay, then what will be the first key? Where the key start? Okay, so the key start is, so 0, 1, 2, 3, 4, 5. So this is sub 5. So this is the starting key. Starting key. Okay, this is a starting key position. Okay, and then what you are going to compare? You are going to see if 17, you measure with gap. So this gap is 5. You are not going to measure with the immediate previous one because this gap is 1. Okay, but we don't care about that. We care about each time the gap is 5. Okay, it's 5. So it's 5. So in this case, is this 2 in its right location? It's not. Is it? So we are going to do the shifting, shift 62 to 17 location, and shift move 17 to 62. Okay. So what we will get is we will get 17 here. And then 83, then 18, then 53, 7. Then here we have 16, 62. Okay. Then we still have 95, 86, 47, 69, 25, 28. Is it? That's the current key. Is it current key with gap size of 5? Then you advance to the next one. Okay, 95. Okay, 95. 95 then, but when you do compare, you need to make sure the gap size is 5. Okay, gap size 5. So is it in its right place? Yes. Is it? So then you advance to the next one, 86. 86, then you compare with the gap size 5. Is it in its right location? Yes, it is in its right location. Is it? So there is no shifting needed. But be careful, over here, each time when you do shift, it's also by the gap size, okay? And then you advance to the next one, 47. Is it? 47 is compare with what? With the gap size, 5. Okay, is it in its right place? No. So you need to do 47 and 53. Is it? And then you move on to the next one, 69. 69, then same thing, you compare with the gap size, 5. Is it? Is it in its right location? It is. Then you move on to the next one, 25. So 25, you compare, it's kind of messy. Let me use a different color. 25 supposed to compare with the gap equals 5, 62. So is it in its right location? It's not. So 25 and 62. Okay, and then you move on to the next one, 28. 28, then you compare with the gap size is 5. So is it in the right? It's not. So 28, 95. Is it? So after, so 17 we have, let me clear it. Okay, then 83, 18, 47, 7, 25, 28, 86, then 53, 69, 62, 95. Is it? So you initialize with gap size this time at 5. Then did you see it does move? You see 25, is it? 28 does get shifted closer to its right location quickly compared with the insertion sort. Is it? Compared with the insertion sort. Okay, so this is the first round with you starting with the gap size. And generally speaking, we pick the gap size. We start with half of your original list size. Okay, and then each gap you decrement by half. By half. So the next round, then you can pick gap size of 3. Okay, of 3. So then this is going to be your current key. And the key is the starting one. Then you always keep moving, is it? And then you keep the gap size. This time is 3, is it? So you compare, you do shifting is every 3 now. Okay, so that's the second round. And then the next round going to decrease to gap size is 1. When gap size is 1 is what? Basically it's a selection sort. Okay, selection sort. So this is called share sort. Okay, and share sorting, the idea is you choose some gap size, is it? So that you can get the out of number move quickly, more quickly to its right location. Okay, and you end with gap size at 1. Okay, so it's the insertion sort. Okay, insertion sort. And then you may see you in the last round you still needed to do insertion sort, is it? And what's the benefit for this? Is it? What's the benefit for this? And regarding the benefits, on one hand, it's you can move the out of number, especially farther away. Is it further away items quicker, getting close to its right place quicker. So that's one benefit. The other benefit is it can save memory. Okay, it's not save memory. It doesn't use as much memory as insertion sort. Okay, because you have an unsorted list and you have kind of a sorted list. Okay, so the memory side. And also it's good for very large number of items. Okay, so it's getting quicker, okay, to move the unsorted to its right location. Okay, so this is regarding share sort. And all the above discussed sorting algorithm, basically they are iterative way, okay, iterative way. So next, what we will see is the next sorting algorithm is called, I will need to use a different set of number, okay, to explain. So the next one is quick sort. Quick sort, okay. And the quick sort is going to use, we call it divide and conquer. Conquer strategy. Okay. And what this divide and conquer strategy means is basically you're going to have a pivot number, okay? Pivot, we call it pivot number. And for the quick sort, you are going to, so we're going to use recursive way. Approach, okay? And around the pivot number, so all of its left numbers going to less than the pivot. So we can call it left sublist. So all numbers in the left sublist must be less than pivot number, okay? But they are not sorted yet. And all the right ones, they are greater than, so this is right sublist. All of the numbers on the right side, they are greater than the pivot number. Okay, and then we keep using this kind of concept applied to the left sublist and the right sublist. So on the left sublist, then you go ahead and do the same thing. You're going to find a pivot number. Okay, then you're going to keep having the left sublist, the right sublist. Same thing here. You're going to have a pivot number. Then you have the left sublist and the right sublist. Okay, and then for each of the sublists, you're going to do the same thing. You're going to have pivot number. You're going to have left sublist and the right sublist. So pivot number, left sublist, right sublist. So pivot number, then left and right. So pivot and then left and then right. Okay, then just think about the case. Okay, so we keep doing dividing kind, each time divide by 2. Is it each time you divide a left sublist, a right sublist. Is it divide by 2 each time? Okay, and just naturally your perspective, when do you think the division should be end? So when this divide by 2, the division by 2 should end by your instinct.
When the sublist can be divisible by 2.
So when the sublist size.
Yeah, can be divisible by 2.
Yeah, so when sublist size is either 1 or 0, there is no more divided, is it? Then you can stop, is it? And when it's stop, what does that mean? Is it mean that it's all going to be sorted just by this diagram visually? Because all it's left, 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 is it? Oh, not here, I'm sorry, shouldn't be. So should write like this. Is it? So visually it can view like this. So when there is no more to be divided by 2, that means what? That means, so you have pivot. You have pivot here. Is it? That means what? That means the whole list is sorted. It's sorted. Is it? So the recursive termination conditions what? The recursive call involves, if you recall, recursive function, whenever you write a recursive method has 2 cases. Is it? Who still remember what are the 2 cases for recursive? You needed to think about it.
Base case
Yeah,
and
base
inductive
case
step.
and the recursive case. Is it? So this is going to be what? This is going to be the base case. Is it? It's going to be stopped because it's a recursive call. Is it recursive call? Okay, so that's a general idea, okay, about quick sort. So quick sort is you divide and conquer, and you can clearly see why we call it divide, because each time you divide by 2. Is it? Until what? Until its size is 1 or 0. That's how in war, is it? If you can get the enemy to size 1, is it? Then it's easy to defeat, is it? To beat your enemy, is it? Okay, so this is a concept of quicksort, just a concept. So next, then let's see, how do you find the pivot and place your pivot at its right location? Is it? How do you divide? How do you divide the left to the right so that the pivot number is at its right location? Is it? So then let's take a look, this sequence of numbers. So I have 75, then I have 95, then I have 26, 39, 43, 62. Next one should be 87, and then 23, then 85, then 57, then 65, then 30. Okay, so this is a sequence number I'm going to apply quicksort. Quicksort. Okay, so in quicksort, one of the very important things is about the pivot number, is it? So in our discussion here, we always going to pick the first number as the pivot. Okay, then you want to divide your list to a left sublist and the right sublist, so that, okay, in this case, it should be 75 here. And then a sequence of number, then a sequence of number, is it? And all the left should be less than 75, and all the right should be greater than 75, okay? So how do I achieve that goal, okay? Let's see if I can erase this part. Okay, good. Okay, then let's get back to. Okay, so in quicksort, as what we just discussed, so it involves around to divide the original list to 2 sublists, is it? So we call that kind of operation split operation. Okay, so how do we do split? Okay, so here is the algorithm for split. So you're going to start your scan. So scan from right first. Okay, and so 30, then you compare with pivot. It's smaller than pivot, is it? Then you stop. Smaller than pivot. You stop here. And then at the same time, you start your scan from right or from left. And when you stop at greater than the pivot number. Okay, so 95 is great, so you stop. Okay, and then we are going to swap these two numbers. So here is 30, here is 95. Okay, then you resume your right scan. It's smaller, so you stop. And you resume your left scan. You need to find, you stop at the one that's greater than the pivot, then you stop. Okay, I stop, then I swap. Okay, so here I have 65, then here I have 87. Okay, and then I resume my scan, so I stop here. And I resume my left scan. I find the one greater, then I stop. Okay, then I need to swap those two. Is it? So 57, then 85. Is it? And then you resume your scan. Let's use a different color. I resume my scan. Is it right scan? So now your right scan already going to go over your left scan. Is it? So you need to stop here. So stop scanning. Okay, stop scanning. And this location should be the place where the pivot is going to be. So you're going to swap this two number. Okay, so I'm going to place 57 here and put 75 here. Okay, so 75 is moved to its right location. Okay, and let me rewrite the sequence of number. Okay, copy it down here. So we have 57, we have 30, we have 26, 39, 43, 62, 65, 23, 75, and then 85, 87, 95. Is it? So after that split operation, that's what you get. Is it? What you get if you take a close look. This is a pivot number. Is it? And all of the left numbers are for 75, they are less than 75. And all of the right numbers are greater than pivot. Are greater than pivot. Is it? So we already divide the original task into two subtasks, kind of. Is it? So 70, so after the split, 75 is in its right location. Is it? Then you can start to do the same thing. Do split again. So split and split to apply to the left sublist and split on the right sublist. Okay, on the right side. Oh, it's going to be hard for me to to do the, let me erase it, okay. And we can try again here, okay. So for the left sublist, for the left, for the left sublist, I pick the first number as a pivot number, is it? Then I'm going to start the right scan. So I stop, is it? And then the left scan. Okay, 62 is greater than 57, is it? So then I need to swap these two numbers. So here is 23, and here is 62, is it? And then I resume. So, the right scan. So I keep doing, so it's a greater, so I shouldn't stop, is it? And I keep scanning, so I'm already at go meet with the left scan, is it? So I should stop here, okay? So you need to stop here, is it? And then this should be the location for the pivot, is it? So I'm going to swap these two numbers. So here is 57, then here is 23, is it? So if we rewrite, let's see clearly, 23, 30, 26, 39, 43, and then we have 57, 65, 62. This is a pivot for the left sublist, is it? And you can see it's split it into the left sublist and the right sublist, is it? And then you can keep doing for the left sublist and the right sublist until each of the sublist size is 1, is it? Then you are done with the split, is it? And you can also see it's going to be arranged in ascending order, is it? So this is the concept of the quick sort, is it? Quick sort. And based on what we just discussed about the quick sort, is it? Quick sort. So you need to do split first, is it? So on the array, is it? And then you recursively call quick sort. Quick sort. Is it quick sort on what? The left sublist. Is it? So here is the quick sort. Is it quick sort? So generally, okay, the pseudocode, you split. Then you quick sort the left sublist. You should also do what? Quick sort the right sublist. Is it? You also quick sort. And so here you have the recursive. You keep calling yourself, but with what? With sublist. Is it? With sublist until your size, the list size is just 1 or 0. There's no more for division. Is it? Then you can stop. Is it? That's why we see quick sort. We apply the recursive concept here to do the quick sorting. So it's divide and conquer. Okay. So this is a general idea about quick sort. Okay, so so I think we covered quite a number of information today. Oh yeah, that's a good question. So have quiz. So today we just have basic concept. So how about let's just don't have quiz. So we are going to have quiz on Thursday, okay? And I don't think I will discuss more new sorting algorithm. It's already five algorithms, so it's going to take a while to get all the information absorbed. So before we complete today's class, are there any other questions? Any questions? And we didn't get a chance to do some exercise, and maybe we can do some small exercise on Thursday, okay, to get familiar on your end about how each of these algorithm works, because today just I'm talking, maybe it's kind of confusing. Any other questions? No more question, everything is good? Okay, if everything is good, then let's just dismiss the class, okay? So I will see you